and due to that we use this process. Okay, recording this started. That's why we use the casting process. We have seen the advantages. What are the disadvantages? Poor surface finish is the most uh, what we can say drawback of this casting process. We need to go for post processing, like machining operation, to get a good surface finish after the casting process. Then what are the applications? Means which products which we can manufacture with the casting process, that we are seen. Then we have studied what are the different terms which we use in casting process, and after that we have studied one by one these terms. Right here, you can see the terms. What is scope, drag? The scope combination of scope and drag is flask, right? Then the parting line, which is in between scope and drag. Then core, which is used to produce the hollow surfaces, hollow parts. Then actual casting, right? Then the gating system, which contains the pouring cup, then screw, runner, riser, and gate, where actually our metal enters into the casting. Right? Then we have the ladle, in which it contains molten metal. We have the furnaces, in which we melt our cast iron or steel, whichever the material which we have. So these are the basic terms which we use in casting. That we also. Then taking the one part of the casting process is the pattern. Right? So pattern is the exact replica of your product with some changes. So we have studied the pattern, like types of pattern, methods by which we make the patterns. Then if we need to manufacture the pattern or we need to fix the dimension, then what design consideration we need to take into consideration, that we have seen. Okay, types of patterns we have seen. What are the types of pattern? Single piece. Single piece, when we use single piece, when the object is very simple, then we use a single piece pattern, right? And when object is somewhat complicated, or if we are not able to produce that in a single, means either in a cope or in a drag, we are not able to produce that. And if you produce, it is difficult to take it out. So in that case, we use the split pattern. We divide our pattern into two parts, right? And once we divide that pattern, so this is the first part and this is the second part. Once we divide that, one part we make in a cope and other part we make in a drag, right? So this is a split pattern. Then we are seeing the cope and drag pattern. So it is similar to the split pattern, but we make cope and drag simultaneously. Right. So here we have the two patterns, and we go for making of cope and drag simultaneously. In earlier case, first we make the cope, then we go for making. Sorry, first we make the drag and then we go for making cope. But in this case, we simultaneously make. So this will increase the production and it will decrease the time for preparing the model. So this is a cope and drag pattern. Then there is a match plate pattern. So what happens in the split pattern? So there is a chances of mismatching of this pattern. Okay. So in some cases, when we join these two patterns, there is chance of mismatching. So in order to avoid and in order to increase the production, we go for using match plate. So this match plate contains the pattern on both the sides, and it also contains the runner. Okay. And by this way, we can reduce our time to prepare the mold. So that's why we use the match plate pattern. Then we have studied the follow board pattern. When our product is of very delicate shape and we want to manufacture this. Now, when we are not using the follow board, what happens? When we ram it, when we ram the sand, so chances of breaking of this pattern is high. And in order to overcome this failure, what we use? We use the follow board. So here you can see this is the follow board. So this will provide the support to the pattern, which is of a delicate shape, and while ramming it, so it will not break. So it will give a support to this pattern. So that is we call it as a follow board pattern, right? Then the loose piece pattern, our part is simple, but it have one or two some complicated shape or some small extended shape. In that case, what we do, we uses this loose pieces. Here you can see A and B. We uses this such kind of loose pieces. What we do, first with the help of loose pieces, we produce the required cavity. Then we use the actual pattern, right? And then what we do, we remove the this pattern actual, and then we go for removing of this loose piece, and we get the required shape. Okay, if suppose it is a single shape, if suppose it is a single shape like this, okay, if suppose this is not a loose piece, what happens, it will remove the sand. So in order to avoid that, what we do, we first remove this part, and then we remove this small loose pieces, and we get the required cavity. All right, then sweep pattern. Generally, if you see the patterns which we have studied before, in that case we use the solid pattern. So as we are using the solid patterns, it consumes more material, right? But if suppose your part is axis symmetric, if suppose your part is axis symmetric, what we do, we use this type of sweep, which is of a single plate. Here you can see the sweep, and by sweeping this 360-degree, we get the required shape. Okay, what is here restriction? We can use sweep pattern only in case when your object is axis symmetric. Right? If suppose your object is axis symmetric, then use this sweep pattern, by which you can reduce your material to prepare the mold. Instead of solid material, solid pattern, you can use the plate pattern. Only single plate we require, right? So that is called sweep pattern. Then there is a skeleton. When there is a large, when there is a large casting, okay, instead of using solid pattern, what we use, we prepare the skeleton. Here you can see the skeleton. In that this skeleton, in the hollow part, what we pour, we pour the loam sand, and once we pour the loam sand, to get the finish, we use this trickle board, and we move on to this, and we will get the full finish of this skeleton pattern. Once the pattern is prepared, with the help of pattern, we prepare the mold, and once mold is prepared, again we remove this sand, or again we use this skeleton pattern. So instead of using large solid pattern of wood, what we are using this sand, loam sand. In the large casting, we use this type of pattern. So these are the types of pattern which we have studied. Then we have studied the materials of the pattern. Which materials we use to manufacture the pattern. So it depends on the type of production. If suppose there is a small batch or piece of production, means one single production, then we prefer the wood as a material. In the wood, we can use white pine, mahogany, and teak. These are the options available in wood material. If suppose there is a large production, so what happens when we use wood in the large production? So wood's dimension get distorted due to the continuous use of this wood pattern. So in order to avoid that error, we go for using the metal, as the metal dimension does not changes due to the repetitive use. For the last production, we select the metal. So some of the non-metallic patterns also we use, like thermosetting, thermoplastic, depending on the type of casting. In investment casting, we use the wax. If suppose there is a large casting, then instead of wood, we go for concrete cast. So these are the materials which we use for preparing of pattern. Then now we have selected the material, we have selected a type of pattern. Now we want to manufacture the pattern. How to manufacture the pattern? So there are different design consideration by which we can prepare the pattern. So which are these? These are the we call it as a types of allowances. It is a shrinkage allowance, draft allowance, machining allowance, shaking or wrapping allowance, distortion or camber allowance. This we are studying. Like, what is shrinkage allowance? When we pour the molten metal into the mold, what happens? It's solidified. And when it gets solidified, what happens? Its dimension decreases. It gets contracted. Due to the contraction, its dimension decreases, and we get the dimensions of casting, less dimensions of casting, which we require. Compared to that, we get the wrong. So that is our wrong casting. In order to get the correct casting, we need to provide this shrinkage allowance. What is shrinkage allowance? Solid shrinkage allowance. After solidifying the molten metal, its dimension decreases. So that shrinkage allowance depends on the type of material, whether it is a cast iron, whether it's cast steel or aluminum. Depending on that, we select the shrinkage allowance. Right? This way also. Then draft allowance. So in this figure, you can understand the importance of draft allowance. When first of all, remember that we provide the draft allowance only for vertical surfaces. Right? Now take the first example. So this is the vertical surface, right? Now, when we remove this pattern from the mold, so it is sticking to the mold wall. Here you can see. So chances of breaking of mold wall is more when we use the vertical surface because it is touching to the mold wall. So in order to avoid that damage, we provide some draft taper to our vertical surfaces. Now in the second case, you can see we can easily remove this pattern from the mold without damaging the mold board. So having this draft allowance, we give the draft allowance to the vertical surfaces in order to avoid the damage of mold board. Right. Then the machining allowance, as we have discussed in the casting, we get the poor surface finish. And if you require the good surface finish, then we need to go for some post-processing operation like machining, grinding of the casted product. When we go for machining operation or grinding operation, its dimension decreases due to as we are removing the material from the part. So to avoid that reduction in dimension, we give some machining allowance to our pattern so that after machining we get the required shape of pattern. So this is machining allowance. Then we have studied the shaking or wrapping allowance. What is this shaking or wrapping allowance? So to get the required mold, what we do, we ram this pattern. So due to ramming, what happens? So whatever the sand around the pattern is there, so that will get closely packed. It will stick to the pattern. Now, when we try to remove this pattern, so it will be difficult to remove that pattern as this sand is closely packed and attached to this our pattern. So in that case, what we do, we simply press this or we shake this pattern and we will try to lose that sand from our pattern. And once it is loose, we remove this pattern. So in this scenario, what happens? Our mold dimension increases due to the shaking of your pattern. So mold dimension increases. So in the pattern, we need to give the shaking allowance by giving the negative dimension so that we get the proper dimension. Right? So this we have seen. Then the last allowance is the distortion or camber allowance. So this is not required for every product. This depends on the size of your part, right? So what happening in this? This is the required, right? But you find after manufacturing or after casting, there is a distortion in casting. So it is distorting in this cast. In every product, we are finding this defect. So in order to avoid this defect, what we do, you give the negative camber. How it is distorting? Suppose it is distorting in this direction, right? So to your pattern, you give the negative camber, right? So you make the pattern like this. Now, when it is get casted, due to the distortion, it will try to expand and it will get the original, right? Instead of preparing the pattern of this shape, if you prepare a pattern of this shape, you are getting distorted. Your pattern is your casting is getting distorted, right? So to avoid that, we already give the camber in. We already give the negative camber so that we get the originals. So this is called distortion or camber errors. Right? This type of pattern we are seeing. What we are studying: types of pattern, material of pattern, and allowances of pattern. Then we have studied the sand, molding sand, which we use to prepare the mold. We have seen the introduction of molding sand, from where we get, what are the ingredients of molding sand like silica sand, clay, moisture, and other material. There is a natural molding sand which we get from the river, or we make the synthetic sand, artificial sand also. Then we have studied this molding sand, types of molding sand. There are different types of molding sand. First three types are green sand, dry sand, and loam sand. What is green sand? When its ingredients are silica sand, clay is 18 to 30%, and water is 6 to 8%. Then this sand is called green sand. We also call it as a fresh sand, right? Now, next is dry sand. What is dry sand? Whatever the mold is prepared with the help of this green sand, we go for baking it. Why we go for baking? In order to get a good strength of mold, plus to remove the moisture. To remove the moisture, we go for baking. So after baking, whatever the sand, molding sand we get, that is called dry sand. Right. Then the third type is loam sand. What is loam sand? It is the combination of silica sand, clay, which is 50%, and water, which is 6 to 8%. Here, clay content is more. Right. When the clay content is 50%, then that sand is called loam sand. And where we use the loam sand, if you remember, just now we have discussed in the skeleton pattern, we use the loam sand. When there is a large casting, then we go for using this loam sand. Okay, so these are the three types. Next types are facing sand, backing sand, system sand, parting sand, and core sand. What is facing sand? So facing sand means what? Whatever the pattern is there. Here you can see the pattern, right? In the pattern, near the surface of pattern, what we do? We pour the fresh sand. Instead of pouring whole fresh sand into the pour, I will give the example. So let's suppose this is your pour and this is your pattern. This is your pour and this is your pattern. So instead of pouring fresh sand all over the pour, only to the face of this pattern we pour our fresh sand. That is a unused sand we use. So this sand is called facing sand. All right. Now, what is backing sand? So remaining portion we use the used sand. Whatever the earlier used sand to produce the casting, that sand we use to just back this sand. Okay. So in this way we can save our sand, fresh sand. Right? Only to the near to the surface of pattern or mold we use the fresh sand, that is called facing sand, and to back the facing sand we use the used sand, that is called backing sand, right? Then the system sand, as I told, in the automatic process we use the system sand. In this there is a no facing or no backing sand. It is the combination of fresh. What is system sand? It is the combination of fresh plus used sand. Some amount of the fresh sand, some amount of the used sand, they are combined and they prepare the mold. That is called system sand. It is used in the automatic process. Then parting sand. So what is parting sand? What we do in the process, here we have the pour and here we have the drag. First we prepare the drag with the help of pattern, then we prepare the mold in the pour like this, right? Now we want to remove this pattern. So in order to remove, we need to remove cope. We need to separate this cope and drag, right? If suppose we have not poured the parting sand here, so what happens? The sand of the cope and the sand in the drag will get attached, will get adhered to each other, and it is not possible to remove that pattern from flask. So in order to avoid that, we pour the parting sand in between cope and drag so that whatever the sand in the cope and sand in the drag will not adhere. Okay, that is the use of parting sand. Then there is a pour sand which we are going to study today. Pour sand is used to prepare the core. And why we use the core? To prepare the internal parts or to have the hollowness in the products. We go for using core. Then we have studied the different properties of molding sand like porosity, flowability, collapsibility, adhesiveness, then cohesiveness, refractoriness. We have studied these different properties. What is porosity? When we pour the molten metal, so it has certain gases. So that molding sand should escape these gases through it. So that property is called porosity. It should enough porous so that whatever the gases or whatever are generated, that should get escaped from this mold. So that is called porosity. This property is. Then flowability. What is flowability? So how good your molding sand flow around the pattern, right? When what we do, we put the pattern, then we pour the molding sand, and we go for ramming of that molding sand. While ramming, that molding sand should go each and every corner of the pattern. It should be flowable throughout around the pattern. Then we call that the molding sand has a good flowability. So this is called the flowability property. Then the collapsibility. Collapsibility is when our molten metal start to solidify, our molding sand should not avoid that path, or it should not restrict the contraction of our solidifying material. Okay, so it should be collapsible. It should crack so that it cannot restrict the solidifying metal. Right. So that is called collapsibility. Then adhesiveness. What is adhesiveness? So adhering to another particle of surface. So we are, let's suppose we are using the split pattern, right? So what is the procedure? I will repeat once again this procedure. So this is the drag, right? Then this is our pattern with one part of pattern. Then what we do, we keep another part of pattern. Then we insert this port, right? So here it is a port and here is the drag. And here is our molding sand. This is our pattern. We prepare like this. Now we need to remove this pattern. To remove this pattern, we need to separate this cope and drag. While separating, whatever the molding sand is there, that should stick to the walls of this cope. Because we are removing this cope and drag, we are moving this. While moving, the molding sand should not fall. It should stick to the surface of cope as well as surface of drag so that it cannot fall. So that property is known as adhesiveness. So the molding sand should have this property of adhesiveness in order to avoid the falling of this molding sand while handling the cope and drag. Then the cohesiveness. Adhesiveness means adhering to the another particle. Cohesiveness means ability to stick together, adhering to each other. That is called cohesiveness. So what is this cohesiveness property? Cohesiveness means, now when we remove this cope, when we remove this pattern from our cope and drag, right? We have the, so suppose this is cope and drag, and we have here mold. right? Now, whatever the sand is there here, so that should not fall into this mold, whatever the sand around this should not fall. It should stick to the sand near to it, so that it cannot fall into the mold and it cannot change the direction. So that property is known as cohesiveness, right? And then the next property is the refractoriness. What is refractoriness? So ability to withstand high temperature. We have prepared the mold with the help of pattern. Here we have prepared the mold. Now we are pouring the molten metal into the mold. Now we know the pouring molten metal have the very high temperature, right, compared to the mold or the sand around this mold. So in that case, it should withstand that high temperature. Withstand means what? What are the temperature of whatever the sand is there here, that should not get fused with that molten metal. So it should withstand that shape and that high temperature. So that property is known as refractoriness, withstanding of high temperature of molten metal. Next, these are the properties which should that molding sand should possess. Right? Now, how to know whether that molding sand have these properties or no? So, in order to test, we have the different testing methods like moisture content test, clay content test, grain size test, and permeability test. These are the tests by which we can identify the properties of the molding sand which we have prepared and which we are going to use to prepare the mold. So this is the permeability test. Permeability test is used to see how porous is your molding sand. So in order to get the permeability number, what we do, we prepare the sample of cylindrical shape. We pass the air, certain amount of air from this sample, and this all air will pass through this and will get escape from another end. Now we will note down the time required for this amount of air to pass through this sample. With the help of that time, we will calculate the permeability number. And with the help of that permeability number, we will decide the porosity of our molding sand. So this is the permeability test. Right. Then we have the next test is moisture content. How to identify the moisture content in the molding sand? What we do, we take certain sample of molding sand, let's suppose 50 gram. So initial weight is what? W1 is a 50 gram. Then we go for baking of that. Baking means heating of that molding sand, what you want, with certain standards. We heat that. After heating, what happens? Whatever the moisture, means water is there in molding sand, that will get evaporated. And due to evaporation of molding water vapor, what happens? Its weight decreases. So we will take the weight after baking. Let's suppose its weight is 48 grams, right? So we will get the difference. Whatever the difference is there, that is your moisture content. Okay, so this is a simple moisture content test. This is the setup for the moisture content test which we have seen. Right. Then the clay content test. Depending on the clay content, if you remember, green sand in which clay content is 18 to 30%. Then the loam sand, clay content is 50%. So how to identify this percentage of clay in your molding sand? For that, we have this instrument. So this is a stirrer. Okay. This is the glass tube in which we pour our molding sand. First of all, we will take the weight. Suppose W1 is a 50 gram sample weight. Then we pour that molding sand into this. Here we have the distilled water. Then we stir this. Due to the stirring, what happens? Whatever the silica sand is there, that will settle down to the bottom of this glass tube. Right? And whatever the clay content is there, that will get mixed with this distilled water, right? So once it is get mixed, we will remove this water, and as we remove this water, what happens? Whatever the clay is there, that will get removed. In some cases, we repeat the process until all the clay is removed from that sand, right? Once we remove that sand, clay from this molding sand, what we get? We get only silica sand at the bottom, right? So we take the weight of that silica sand. That weight is known as WT. Let's suppose that weight is 40 gram. So what was the initial weight of molding sand? 50 gram. And what was the weight after doing the experiment? It's a 40 gram. So 10 gram is your clay content. Means what? 20% is the clay content. Hence we can conclude that 20% clay is there in our molding sand. So this is how we find out the clay content. So this is the procedure. And then the grain size test. Right. What is the grain? Just wait. What is the grain size test? To find the grain fineness number of our molding sand, we go for this type of test, that is a grain size test. Here we have the different sieves, 7 or 8, right, which have different size of meshes. We pour our molding sand into the top sieves. Top sieves, here you can see. So this is the machine. In the top sieve, we pour our molding sand or sample molding sands. Let's suppose 50 grams, right? And then we start this siever machine, and due to the shaking of this, whatever the small particles are there, that will get fall down, and that will get collected into the respective size of sieves, right? And then we take the measurement of each sieves, and depending on the measurement, we decide the grain fineness. That part we are seeing. So here there are different sieves number, multiplier is there, and with the help of that we find the grain fineness. Okay. Then we have the molding sand, we have the molding properties. Now we want to make the mold. So which practices of molding we carried out generally? So these are the practices: green sand, dry sand, and phase dry. Phase dry is the out of syllabus. Green sand and dry sand is for our syllabus. What is green sand? Fresh sand, which contains 18 to 30% of clay, 6 to 8% of water. So that sand we call it as a green sand. When to manufacture any product, we use such type of sand which contains 18 to 30% clay, 6 to 8% water. Then that molding is called green sand molding. Now, if suppose we require a good strength of mold, good strength mold, then what we do, whatever the mold which is prepared by the green sand, we go for baking of that complete core and dry, right? In order to remove the moisture content, plus to get a good strength, we go for baking. After baking, whatever the mold we get, that is called dry sand molding, right? Now, in some cases, we go for phase drying sand. So what we do in dry sand, entire core and dry, we bake it or we heat it. But in the phase dry molding, what we do, let's suppose this is a dry and this is the mold which we have prepared with the help of pattern. So with the help of torch, we only heat the surface of this mold. Instead of heating entire this dry, we only heat the face, right? And we get the good strength at the face. In order to save the cost, and save time, we can go for phase dry cell. Okay. This is the type depending on the use. Then there is a pit molding, floor molding, and bench molding. So depending on the size, I have explained it with the help of example. Right, when the small casting is there, then we manufacture it on the bench. When large casting is there compared to this, we manufacture it onto the floor. Right. So this is the bench. This is the floor casting. When there is a very large casting, then we go for pit molding. We go for pit molding. So these are the depending on the size of casting, we decide the molding process. Pit molding, floor molding. Then the two different types of molding practices are shell molding and permanent molding. What is shell molding? Here you can see the shell molding. This is our required shape. Let's suppose this is our required shape. So we prepare the metal pattern of this required shape, right? And we heat this metal pattern. Then here you can see in this first step, here there is a sand which contains binder plus sand, and our pattern is heated. This is our hot pattern. What we do in the second step, we invert this system. Once we invert, as our pattern is heated and the sand contains binder particle, so it will stick to our pattern, metal pattern, right? So the thickness of that is depend on the time which we allow for sticking, right? Once we get the required thickness, again we invert it and get it to original position. So here we can find the shell which we have prepared. Same process we repeat to get the other part of shell. This is the one part, and by repeating the process, we get the another part, and then we join these two parts of shells, and we get the mold. And in that mold, we pour the molten metal, and we get the required casting. And once the casting is solidified, we break this, and we get the final product. Right. So this is shell molding. So same here, you can see the shell molding process. Metal pattern which is heated. So this binder and silica will get stick to this, and we will get the one part. After repeating, we will get the another part, and by joining this, we will get the mold. And in that mold, we pour the molten metal. And once they solidify, we get the final product. So this is the shell molding. And the last type of molding is a permanent molding. So in the name, it is permanent. What is permanent? If you compare to the other molding process which we have just seen, in that we prepare the mold, we pour the molten metal, right? Once the molten metal gets solidified, we break that mold in order to remove that molten metal, right? We break that, but what happens when we break? Again we need to make the mold, again we need to pour, so that consumes more time, plus it also consumes more cost. So in that case, we go for permanent mold if you want to reduce your cost and time. Here you can see the permanent molding process system. Here we have one stationary mold and one movable. Now, suppose we are using for the first. What we do, we spray some liquid or oil to the surface of this mold. Why we? In order to avoid sticking of molten metal to the walls of permanent molding, we spray some oil. After spraying, we close this by moving this piston, right? By moving this piston in this direction, we close this. Let's suppose after closing, we get this, right? And we pour the molten metal into this. So molten metal will get filled into this cavity. And once it is solidified, we move this movable mold section with the help of this piston and cylinder, right? And we will take out our final product. So in this case, to remove the final product, we need not to break our mold. That's why it is called permanent molding. But what is the restriction here? In this, we can manufacture only the aluminum or the metal which is having less temperature. Why? Because we are preparing or we are manufacturing the mold sections with the help of metal, and that metal should have high temperature of the metal which we are manufacturing. So that is the restriction. But in other type, in suppose casting, we can manufacture any product. But in this, the metal which have less temperature, that we manufacture. So this is the permanent, right? So this part we have studied up to the last time, and I feel it is necessary to explain this because as we have more gap. So you have any doubt? Actually, it took more time, 50 minutes. Okay, no problem, but it was necessary. Have you understood already? We have studied already this, but just I explain to recall or to review all whatever we have studied. Any doubt?
No, sir.
No, sir.
So it is 10:52, and as core is the new topic, shall I continue this or shall I take it tomorrow? I think tomorrow at 1:30 p.m. we have the lectures. So as the time is only 5 to 8 minutes, we will take this part in tomorrow's lecture, right? So I will take the attendance. That core part we will start in the next lecture, and I think 3 lectures we have in this week. In 3 lectures we will finish this. Only core part, core and melting furnaces. In 1 lecture that will finish. In 1 lecture we will study the gating system, and in 1 lecture we will study the problem related to the gating system. And very simple problem related to the gating system. We'll try to finish in this. Any doubt? Do you find these lectures useful? Means whatever we have conducted, because I just repeated all this. Do you find this is useful?
Yes, sir. Yes, sir.
Yes, sir.
Uh, we will meet again tomorrow for our next. Okay, thank you. I have taken the attendance. You can leave.